I was actually driving the other day, and I found myself just staring at the gauge on the dash.
The battery percentage, I'm guessing.
Yeah, exactly, the
Yeah.
battery percentage. And I had this weird moment of nostalgia. Because remember when the whole conversation about the future of cars was just, it was
I
simple,
was incredibly simple, just binary.
right? It just felt like flipping a switch. You just turn off the gas pump and you plug it into the wall. Easy.
The early EV phase, it really was a simpler time for the industry.
It was a scramble, though, right? Like
Yeah.
every single automaker out there was just trying to shove a battery, honestly, any battery into whatever chassis they had lying around
Yeah.
and just get it on the road before they got left behind.
The era of the retrofit. We
Yeah.
saw a lot of that.
Yeah, the retrofit era.
Yeah.
But I'm looking at this massive stack of reports you brought in for us to go through today. And I get the distinct feeling that the simple era is completely over.
It is entirely over. We're hitting a wall. Or to be a bit more precise about the data in front of us, we are hitting a massive strategic inflection point right now. Okay.
We are looking right at the horizon line of 2026, and the data across all these source materials is just screaming one specific thing. The one-size-fits-all approach is dead. When you say one-size-fits-all, you mean the idea that you just build a flat skateboard chassis, put a huge lithium battery in the floor, and slap whatever body you want on top of it.
Correct. That exact method. It has hit its absolute physical and economic limits.
Really?
Yes. Because you can't just keep making batteries bigger and bigger just to get more range. Eventually, the car gets way too heavy, the tires wear out in 10,000 miles, and the cost just skyrockets to the point where no one can buy the thing.
Makes sense.
So we are entering a totally new era. The technical term we are seeing in the research is multi-energy symbiosis.
Multi-energy symbiosis. I mean,
Yeah.
that sounds like something out of an advanced biology textbook, not a car manual.
It is surprisingly biological when you dig into it. It means the powertrain isn't just a single big battery anymore. It is a highly complex matrix of different technologies. And they are chosen based on total cost of ownership, what we call TCO, and the specific infrastructure maturity of a region.
So it's about fitting the organism to the environment, basically.
Exactly. You don't put a polar bear in the Sahara. And similarly, you wouldn't put a massive, expensive solid-state battery into a cheap urban commuter car.
Right, right. So we're not just talking about building a marginally better electric car here. For you listening, this means we are talking about a fundamental fracturing of the entire vehicle market into a highly specialized species of cars.
Precisely. And because this transition is so incredibly complex, we really cannot just ramble our way through these source reports. We need a very strict structure for this deep dive.
I know where you're going with this.
I want to use an MECE approach today.
MECE. You know I love it when you bring the top-tier management consultant energy to the table. Mutually exclusive, collectively exhaustive.
It's the only way we're going to survive this data dump without getting lost. We are going to strictly break down the 2026 vehicle into 7 distinct critical subsystems. Mutually exclusive meaning no overlap. Collectively exhaustive meaning if we cover these 7, we have covered the entire future of the automobile.
Yeah, I love a good top-down roadmap. Lay out the 7 pillars for us. Where do we start?
We start at the absolute core. Number 1 is storage, which is the whole battery revolution. Number 2 is intelligence, the battery management system, or BMS.
Got it.
Number 3 and 4 cover the muscle of the car. That's the drive system covering motors and inverters. Number 5 is the grid connection. Number 6 handles the heavy lifters, which is the hydrogen story. And finally, number 7 is the glue holding every single piece together, thermal management.
7 pillars. Okay, let's just dive right into the big one, the beating heart of the whole thing. Section 3.1 in our source material, the battery.
Right, the storage core.
Now, I got to be totally honest with you here. If you've been following this space, we've been hearing about revolutionary battery breakthroughs every single week for like a decade.
Oh, absolutely. The boy who cried solid state.
Exactly. Solid state is coming next year has been the headline since like 2015. So why should I or anyone listening actually believe that 2026 is any different? Is this just more vaporware?
That skepticism is entirely healthy. The hype cycle in battery tech is notorious. But here's the critical difference this time. We are finally seeing the divergence in the actual physical supply chain orders. The industry is actively splitting. It is basically a divorce in the battery family.
A divorce, okay. Who's getting the house and who's taking the kids?
On one side, you have the path of extreme performance. That is where solid-state batteries, or SSB, reside. And on the exact opposite side, moving in a totally different direction, you have the path of extreme cost efficiency. That is sodium ion.
Let's tackle the high-end luxury side first. Solid state. Walk me through the actual physics here. Why is a solid battery inherently better than a liquid one?
It basically comes down to two primary factors: safety and density. In the standard lithium-ion battery sitting in your phone or your car right now, the electrolyte, which is the medium the ions actually swim through to create power, is a liquid solvent.
Right.
It is organic, and more importantly, it is highly flammable.
Which is why we see those horrific dash cam videos of EV fires that look like military flares going off on the highway.
Exactly. If that liquid gets punctured in a crash, or if it severely overheats, it burns aggressively. But there is a much more insidious problem happening inside the battery called dendrites.
Dendrites, those little microspikes. Okay.
Imagine looking inside a battery at the microscopic level. As you charge and discharge, the battery lithium ions move back and forth between the anode and the cathode.
Like commuters going to work and coming home.
Perfect analogy. But sometimes, instead of settling down smoothly when they get home, the lithium atoms start to plate unevenly. They bunch up, they start forming these microscopic needle-like structures, little stalactites growing directly from the anode and reaching across toward the cathode.
And if that needle manages to touch the other side,
You get a short circuit, a spark inside a flammable liquid, boom, total thermal runaway.
yikes.
Now here is the magic of the solid-state architecture. If you replace that flammable liquid with a solid ceramic or a solid polymer electrolyte, it is physically rigid. It literally blocks the dendrites from growing.
Because it's solid.
Right. It's like trying to push a sewing needle through a solid brick wall versus pushing it through a glass of water. It just fundamentally suppresses the growth.
So because it's physically so much harder to short out, you don't need as much protective casing and you can just pack the raw energy in tighter.
Much tighter. The reports are showing energy density numbers hitting 400 to 500 watt-hours per kilogram by 2026.
Wow.
To give you context on that, a standard Tesla Model 3 battery on the road today is roughly 260. So we are looking at virtually doubling the total amount of energy sitting in the exact same physical footprint.
I mean, that's the difference between a 300-mile range and a 600-mile range.
Mm-hmm.
That completely changes the value proposition of an EV for the average driver.
Mm-hmm.
But again, I have to press you on the timeline here. You said 2026. Is that actual mass production reality?
It is quote-unquote semi-real, and I mean that quite literally based on the strategic roadmap. The material highlights the era of semi-solid batteries as the critical bridge for the 2024 to 2026 window.
Semi-solid. I mean, that just sounds like a compromise. If solid is the holy grail, why wouldn't a car maker just wait a couple more years for the real thing?
Because manufacturing the real 100% solid thing is absolute hell right now. Solid electrolytes are incredibly finicky to work with at scale.
How so?
Well, for one, some of them are incredibly sensitive to ambient moisture in the air. You have to build them in these massive, ultra-dry, clean rooms. But the bigger issue is interface resistant.
Interface resistance, meaning where the parts touch.
Yes. Basically, the solid electrode and the solid electrolyte don't physically mate well enough to let electricity flow efficiently. Since they are both rigid solids, there are microscopic air gaps between them. It is like trying to rub two dry rocks together to conduct power. It's terribly inefficient.
So semi-solid is like the cheat code for manufacturing.
It's the pragmatic engineering fix.
Yeah.
You use the solid ceramic structure for safety and density, but you wet it with a tiny, minuscule amount of liquid electrolyte, maybe 5 to 10%, just enough to fill those microscopic gaps and make that electrical connection work.
It's like licking a suction cup before you stick it to a window.
That is a very vivid and surprisingly accurate image.
Yes.
And it works brilliantly in the real world. Look at what Wellion and NIO are doing. They are already actively deploying a 150 kilowatt-hour semi-solid pack. It's achieving a 1,000-kilometer range in testing. That is hardware hitting the road now, not a lab experiment for 2030.
1,000 kilometers. That's what driving from San Francisco to Portland without stopping to plug in once. That essentially kills range anxiety dead in its tracks.
It completely eliminates it. But there is another massive piece of the chemistry puzzle mentioned in this storage section that we have to talk about: silicon anodes.
Yeah, I saw that highlighted in the text. Engineered silicon. Now, my understanding was always that graphite was the gold standard for the anode side of a battery. Why are we messing with silicon?
Graphite has been the standard for decades. But think of a graphite anode like a bucket that is practically full at this point.
Right.
We have optimized it to its physical limits. We really can't squeeze much more lithium into that specific molecular structure.
Okay.
Silicon, on the other hand, is an incredibly greedy host material. A silicon atom can hold up to 10 times more lithium atoms than a graphite atom can.
10 times. So why haven't we been using silicon this whole time?
Because when silicon absorbs all that lithium, it gets fat. It swells up massively. It expands by about 300% during the charging cycle.
100%, it just balloons
It's
up.
massive swelling. Imagine if the gas tank in your car literally tripled in physical size every single time you filled it up at the pump. It would crush the frame of the car. Inside a tightly packed battery cell, this aggressive swelling physically crushes and cracks the internal structures. The silicon pulverizes itself, and the battery basically dies after just a few dozen charge cycles.
So how are the engineers fixing a fundamental swelling problem like that?
This is where the engineered part of engineered silicon comes in. The report details a process where they create porous carbon skeletons.
Skeletons.
Think of it like a rigid microscopic sponge or a cage. They embed the silicon particles deep inside this hollow carbon cage. When the silicon absorbs the lithium and expands, it expands inward into the empty voids of the cage rather than expanding outward and breaking the battery casing.
That is incredibly clever material science.
It is brilliant. And the strategic value here isn't just density. This specific structure unlocks 4C fast charging.
4C meaning 4 times the capacity rate.
Yes. Because silicon can absorb those lithium ions so incredibly fast, we are looking at going from 0 to 80% charge in under 15 minutes.
That's practically the time it takes to go to the bathroom and grab a coffee at a gas station. So that handles the high-end luxury side. That's the Porsche and the high-end NIO territory.
Huh?
But what about the rest of us? You mentioned a strategic hedge earlier. Sodium ion.
This is honestly my personal favorite topic in the whole matrix because it touches on global geopolitics just as much as it does chemical engineering. Right now, the entire automotive world is fundamentally addicted to lithium.
Which is largely refined in 1 or 2 countries.
Exactly. The supply chain is a massive bottleneck. Lithium is expensive, the mining is complex, and the price volatility is a nightmare for a car company trying to forecast costs. Now, do you know what sodium is?
I mean, it's salt.
It is literal salt. It is everywhere on Earth. We have literal oceans full of it. It is dirt cheap to acquire and refine.
But isn't it heavier? I vaguely remember from high school chemistry class that sodium sits directly below lithium on the periodic table. It's a much bigger atom.
It is significantly heavier and physically larger. That is the fundamental trade-off. The overall energy density is much lower. We were talking around 140 to maybe 160 watt-hours per kilogram.
Okay, so you are definitely not going to see a sodium-ion sports car setting track records.
Never! But for a cheap A-class city car, a local Amazon delivery van, a commuter scooter, it is absolutely perfect. It is the economically superior battery for the masses.
It's the good enough battery.
Yes. But here is the kicker. It has one specific superpower that lithium completely lacks. Unbelievable cold weather performance.
Oh, explain that. Because, I drive an EV right now, and it absolutely hates the winter. If it drops below freezing, I lose like 30% of my range just driving to the office.
That is the curse of lithium chemistry, specifically the cheaper LFP or lithium iron phosphate batteries that a lot of standard range cars use. When it gets freezing cold, the liquid electrolyte thickens up like molasses. The lithium ions just get sluggish and can't move efficiently.
Right.
Sodium ions, despite being physically larger atoms, actually move through their specific electrolyte much easier at extreme low temperatures. A sodium-ion battery easily retains over 90% of its usable capacity at minus 20 degrees Celsius.
Minus 20. That is a total game changer for places like Canada or Norway or Minnesota.
It fundamentally solves the winter range anxiety problem for the mass market without needing an expensive heating system. And from a strategic corporate level, it gives every major car maker a legitimate plan B.
A strategic hedge.
Exactly. If the price of lithium suddenly spikes again, like it did back in 2022, a company can just smoothly pivot their entire lower-tier vehicle lineup to sodium. It de-risks and stabilizes the whole industry.
So we've got the raw chemistry laid out. High-end solid state on one side, low-end sodium on the other. But before we leave the battery section, I want to ask about how these actual cells are physically put into the vehicle. The report uses these acronyms, CTB and CTC.
This is where the pure chemical engineering meets mechanical engineering. We are shifting from the old cell-to-pack model to cell-to-body and cell-to-chassis.
Meaning the battery is no longer just a big, heavy box that you slide under the car.
Right. Think about the old legacy way of doing this. You have individual battery cells. You bundle those into a module. You take a bunch of modules and bolt them inside a heavy steel pack. Then you bolt that massive pack onto the chassis of the car. It is like a set of heavy, expensive nesting dolls. There is so much wasted metal and dead weight.
And the new way removes all those layers.
They call it a sandwich structure. The BYD seal is the prime case study in the report. They got rid of the pack entirely. The top cover of the battery casing is literally the floor of the cabin where you rest your feet.
Wow.
And the battery cells themselves are actually load-bearing components. They are structural. They are physically holding the car together and handling the twisting forces as you drive.
Okay, I have to play devil's advocate here. If the actual battery cells are acting as the frame of my car, what happens if I get T-boned in an intersection? Or even just get into a really bad fender bender? Does a dented quarter panel mean my entire car is totaled because the battery frame is technically compromised?
That is the billion-dollar insurance question right there.
Yeah.
From a strict manufacturing and performance standpoint, it is completely brilliant. It drastically lowers weight, increases the torsional stiffness of the car, and cuts production costs.
But the repairability?
From a repairability standpoint, it is a complete nightmare. You are spot on. If the battery is structural, you can't just easily unbolt and swap out a damaged module. A moderate crash might mean you have to write off the entire vehicle value.
That sounds like insurance premiums for these cars are just going to skyrocket to cover that risk.
It is the ultimate trade-off. You are getting a cheaper, lighter, longer-range car up front at the dealership, but taking on potentially higher financial risk on the back end.
Yeah.
Which is exactly why the intelligence layer of the car is becoming so critical. You as the owner or the insurance company need to know exactly how much structural or chemical damage that battery has taken after a bump, which perfectly transitions us to pillar number 2, section 3.2, the BMS.
The battery management system. Let's get into it.
Yes. In the past, the BMS was essentially just a dumb safety switch. It just asked, is the battery too hot? If yes, turn it off. Now, it is actively evolving into a highly dynamic AI brain that controls the entire energy flow.
I noticed the report dedicates a huge section to something called Shannon entropy. Now, I vaguely know what entropy is from high school physics, right?
Yeah.
It means chaos or disorder in a system. But what on earth does Shannon entropy mean inside a car battery?
It is a really fascinating application of pure information theory. Let me use an analogy. Think of a massive EV battery pack, like a gigantic public library.
Okay, a library.
When the library is officially closed at night, which represents when your car is parked in your garage, it should be perfectly silent in there. Total equilibrium.
Total silence. Makes
Yeah.
sense.
If you measure the voltage of all the thousands of cells, they should be completely stable. But let's say one single cell out of thousands has a tiny microscopic manufacturing defect, a microshort.
Okay.
It is basically like one single person hiding in that massive dark library whispering to themselves. It creates a tiny, tiny bit of electrical noise.
But in a massive 80 kilowatt hour battery, wouldn't that tiny whisper just get completely lost?
But that is exactly the problem. When the car is actually driving down the highway, meaning the library is open and full of people, there is way too much chaotic electrical noise to ever hear that tiny whisper. You can only detect it when the car is in a deep resting phase.
I see.
Shannon entropy is a highly sensitive statistical mathematical tool that the BMS uses to measure that exact uncertainty or noise in the voltage distribution while the car is asleep.
So the car literally wakes its own computer up at like 3 a.m., listens for a tiny electrical whisper, and says, cell number 402 is acting a little weird.
Precisely. It is detecting microshorts with a resistance as incredibly high as 10,000 ohms. To be clear, these are microscopic faults that are definitely not going to cause a fire today or even tomorrow, but they are faults that might evolve into a thermal runaway event 6 months from now.
That is incredible. It fundamentally changes vehicle safety from being purely reactive to highly predictive.
And it doesn't just do this on the local computer, it links all this data directly to the cloud. This introduces the concept of the digital twin.
The digital twin, the ghost in the machine.
Quite literally, yes. Your physical car constantly streams its telemetry data up to a cloud server. In that server, there is a virtual exact software simulation of your specific battery pack. Not a generic model of that car, but your exact battery.
Yeah.
It runs something called PNN, physics-informed neural networks. It constantly simulates and predicts exactly how your specific battery is chemically aging based on how aggressively you drive, how often you fast charge, the temperatures you park in, all of it.
But why go to all that massive computational trouble for every single car on the road?
Two massive commercial reasons. Number one is RUL, remaining useful life. The AI can predict exactly when your battery will reach its end of life with an error margin of less than 1.5%.
That's incredibly precise.
And number two, which is arguably the biggest commercial value proposition, is resale value.
Ah, the battery passport concept.
Exactly. Think about it. If you try to sell a used EV on a lot today, the buyer is naturally terrified. They look at it and go, is this battery junk? Did the previous owner ruin it by fast charging it to 100% every single day?
Right. You have no way of knowing just by looking at the tires.
You don't. But with a cloud-backed digital twin, you hand the buyer a certified cryptographically secure digital certificate, a battery passport. It proves the exact state of health of that specific battery pack.
That makes total sense.
Yeah.
It is literally just Carfax, but for battery chemistry.
It instantly turns a massive unknown liability into a highly verified financial asset. And this cloud connection also heavily enables the shift to WBMS, wireless BMS.
Wait, wireless. As in wireless communication inside the actual sealed battery pack.
Yes. Think about the physical wiring harness inside a traditional battery pack. It is an absolute mess of orange copper spaghetti routing to every single cell to monitor voltage.
Right.
If you stick a tiny wireless transmitter chip on each cell module, you can literally delete 90% of that low voltage wiring harness.
But isn't a wireless signal inherently, I don't know, unreliable? What if outside electromagnetic interference blocks the signal on the highway? You absolutely do not want your battery cells suddenly losing connection with the central brain, right?
That was the major engineering fear for years. But they have solved it by using heavily proprietary 2.4 gigahertz protocols. It is conceptually similar to Bluetooth, but infinitely more robust and secure. They test these protocols in the most extreme, noisy electromagnetic environments imaginable to ensure the signal never drops.
And I'm guessing deleting all those wires saves a ton of weight.
It saves weight, but the real benefit is factory automation. A robotic arm can assemble a fully wireless battery pack in half the time it takes a human because the robot doesn't have to delicately plug in 100 tiny, fragile plastic connectors.
Efficiency again. It literally always comes back to cutting out weight and cutting labor costs. All right, so we have thoroughly covered the energy storage and we've covered the AI brain. Let's move to the physical muscle of the vehicle. Pillars 3 and 4, section 3.3 and 3.4, motors and inverters.
This is the absolute domain of the silicon carbide revolution, SiC.
I feel like SiC is the ultimate buzzword of the decade in EV engineering circles right now. But for the listener, let's really get into the weeds on this. Why is silicon carbide fundamentally better than just standard silicon?
It all comes down to a property in physics called the band gap.
Okay, you're going to have to explain band gap to me like I'm a 5-year-old.
I can do that. Imagine an exclusive nightclub. The electrons flowing through the chip are the people partying inside the club. The band gap is the bouncer standing at the front door trying to keep them all contained inside.
Okay, I'm with you.
In standard legacy silicon chips, the bouncer is honestly kind of weak. If the nightclub gets too hot, meaning the temperature of the chip rises, or if the music gets way too loud, meaning the voltage spikes, the bouncer gets overwhelmed. He gives up, the doors fly open, and the electrons just start leaking out all over the place where they shouldn't be.
So the chip just crashes or shorts out.
It physically fails, or it leaks massive amounts of electrical energy as pure waste heat. Now let's look at silicon carbide. It is known as a wide bandgap semiconductor.
So the bouncer is bigger.
The bouncer is an absolute giant. It takes roughly 3 times as much raw energy to knock those doors open.
Got it. So silicon can just handle way more heat and pressure?
It can literally handle 10 times the breakdown field strength of standard silicon. It can operate perfectly at massively higher temperatures without leaking any energy. And this specific physical trait is exactly what allows the entire auto industry to finally move to 800-volt electrical architectures.
Right, the 800-volt standard, we already see this on the ultra-high-end stuff, right? The Porsche Taycan, the Audi e-tron, some of the newer Hyundais. Why exactly is 800 volts the magic number everybody is chasing?
It is pure Ohm's law. Power equals voltage multiplied by current.
Okay.
If you are an engineer and you want to push more power to the wheels or charge the car faster, you only have 2 choices. You can either increase the current or you can increase the voltage. But in electrical engineering, current is the ultimate enemy.
Why is current the enemy?
Because high current physically creates massive amounts of heat through resistance, and to handle high current safely without melting the car, you have to use incredibly thick, heavy, expensive copper cables.
So if you just double the voltage from the old 400-volt standard, Up to 800 volts, you can cut the current right in half to deliver the exact same amount of power.
Exactly. You get thinner cables, you drop a ton of vehicle weight, and you enable ultra-fast charging without melting the plug. But here's the catch. Standard silicon chips simply cannot handle rapidly switching 800 volts on and off efficiently. They just fry.
But the giant bouncer, the silicon carbide, handles it no problem.
SiC handles it effortlessly. The end result of swapping to SiC is an inverter that operates at roughly 99.5% efficiency.
99.5%. I mean, that is basically mathematically perfect.
It is as close to perfect as physics allows. And that massive efficiency gain translates straight to the wheels. Just by changing out the material of that one specific chip in the inverter, you immediately give the car a 5 to 10% boost in total driving range. It is literally free range unlocked by material science.
It's not exactly free, though, is it? From what I've read, SiC is insanely expensive to manufacture.
It is brutally expensive. Growing high-quality silicon carbide crystals in a lab is incredibly difficult and slow. It literally takes weeks in a high-temperature furnace just to grow a single crystalline boule that is maybe a few inches tall. It is almost like trying to artificially grow a flawless diamond.
So if it's that expensive, how are automakers actually going to make it affordable for a standard $30,000 commuter car?
They engineer their way around the cost. They cheat a little bit. The report discusses a really smart approach called the hybrid switch strategy.
Hybrid chip.
Basically, you don't use the ultra-expensive series for every single electrical pathway. You strategically pair one expensive series chip with several cheap traditional silicon IGBT chips. You use the series only for the ultra-high-speed switching tasks where you desperately need that efficiency. And you use the cheap silicon chips to handle the dumb heavy lifting of just conducting the raw current once the switch is open.
That's fascinating. A hybrid switch strategy for a hybrid world.
Exactly. Or they use specialized circuit designs called T-type topologies. Without getting too bogged down in the electrical engineering, it is essentially a very clever way of arranging the circuit, so you can safely split a massive 800-volt load across multiple, much cheaper chips instead of forcing one massively expensive series chip to take the whole hit.
Really clever cost optimization. Now, looking at the mechanical side of the motors, I saw a term in the report that caught my eye. Silver sintering. Is that just a fancy marketing term for high-end soldering?
It is basically soldering on steroids. It is absolutely necessary now. Think about normal lead or tin solder used on circuit boards. It naturally melts at a relatively low temperature. But as we just discussed, these new SiC chips are designed to run incredibly hot.
Right.
If you use regular standard solder to attach a SiC chip, the extreme thermal cycling, heating up and cooling down every time you drive, would cause that solder to quickly suffer from thermal fatigue. It would literally crack and fail after maybe a few years of hard driving.
Just like bending a paper clip back and forth until it eventually just snaps in half.
Perfect analogy. Yes. Sintering solves this completely. They use a specialized nano-silver paste instead of solder. Under high pressure and heat, it doesn't just melt on top of the metal, it physically diffuses its atoms directly into the copper structure. It creates a seamless, unified bond that is roughly 20 times more durable than any traditional solder.
20 times more durable. I guess you need that kind of durability because these electric motors are just being pushed harder than they've ever been before.
Much harder, especially because we are seeing an intense industry trend toward extreme physical integration. The report highlights the move to 12-in-1 electric drive units.
12-in-1?
Yeah.
Honestly, that sounds like a cheap men's body wash shampoo combo, not a car part.
It really does. But it represents the ultimate engineering integration. They're taking the drive motor, the inverter, the transmission reducer, the onboard charger, the DC to DC converter, the BMS, the vehicle control unit, and all the complex thermal management valves and cramming them all into one single highly compact metal housing.
Wow, all in one box. But wait, just logically speaking, think about the heat that must generate. You have all of those high-power components generating waste heat inside one tiny enclosed box. Air cooling is absolutely not going to cut it.
Air cooling is useless here, and honestly, standard water cooling jackets aren't even enough anymore to pull the heat away fast enough, so the industry is moving aggressively to direct oil cooling.
Direct oil cooling, how does that work?
They are actively spraying specialized dielectric cooling oil directly onto the exposed raw copper windings of the motor itself, the parts we call the hairpins.
That just sounds violent. You're just spraying pressurized oil directly onto high-voltage electronics while they're spinning at 15,000 RPM?
It sounds chaotic, but it is highly, highly effective
Mm.
because the oil physically touches the exact copper wire that is generating the heat. It pulls the thermal energy away instantly, directly from the source.
Okay.
And the major consumer benefit here is sustained performance. You know how if you take some older EVs to a track day and drive them hard for a few laps, the computer suddenly cuts your power because the motor is overheating.
Yeah, it's called durating, right? It's incredibly annoying if you're trying to have fun.
Direct oil cooling practically eliminates durating. You can push the car to its absolute peak power limit for vastly longer periods of time without cooking the motor.
All right, so we're flying down the highway, oil spraying everywhere inside the housing, running at 99% efficiency. But eventually we do have to pull over and put energy back into the system. Let's talk about the grid, pillar number 5, section 3.5.
The grid connection. This is conceptually where the car physically stops being just a vehicle and transforms into a functional node on the macro energy network.
A node in the energy web.
Exactly. We just spent all that time talking about silicon carbide for the main traction motor. But for the actual onboard charger, the OBC, the component that takes AC power from the wall at your house and turns it into DC for the battery, there is a completely different semiconductor taking over. Gallium nitride, GaN.
GaN. I actually recognize that. I've seen GaN advertised on those really tiny, ultra-fast laptop chargers you can buy online.
That is the exact same underlying technology, just scaled up for a car. GaN's ultimate superpower is switching speed. It can cleanly switch power on and off at megahertz speeds. We are talking millions of times per single second.
But why does the sheer speed matter for charging a battery? Does it make the car charge faster?
Not exactly. It matters because of the heavy magnetic components inside the charger, the copper transformers and the inductors. The physical size of those heavy magnetic parts is inversely proportional to the switching frequency.
Okay, so the faster the chip swishes, the smaller those heavy metal parts can be.
Precisely. By moving to GaN chips operating at megahertz speeds, engineers can literally shrink the physical size and weight of the entire onboard charger by up to 50%.
So again, we are cutting weight, which adds range. But reading the report, the much bigger strategic story in this section isn't just about making the charger smaller. It's about V2X, vehicle to everything.
Yes. This is the ultimate techno-economic dream of the prosumer. You aren't just a consumer of electricity anymore, you are a producer and a trader.
Energy arbitrage.
Exactly. Picture this. You come home and plug your car in at 11 p.m. Wind power on the macro grid is blowing strong, demand is super low, and electricity is practically free. Your car fills its battery at rock-bottom prices. Then the next day at 6 p.m., everyone in your city gets home from work, turns on their air conditioner, starts cooking dinner, and peak grid demand spikes the price of power. Your car, realizing the price is high, actively reverses the flow and starts selling that cheap energy it bought last night back to the grid at a massive premium.
You literally buy low and sell high automatically while the car is just sitting in the driveway doing nothing.
It is fully automated energy arbitrage. But it completely relies on a very specific new software protocol standard called ISO 1511820.
Catchy name. What does that protocol actually do?
It acts as the universal translator between your specific car and the macro power grid. It enables two massive features. The first is BPT, which stands for bidirectional power transfer. That standardizes exactly how the car pushes power back into the grid safely.
And the second feature?
The second is PNC. Plug and charge.
Oh, I love plug and charge.
It is the ultimate user experience. No more fumbling with 3 different charging apps on your phone or swiping a credit card in the rain. You just plug the heavy cable into the car and you walk away.
The car just handles the negotiation on its own.
Yes. The protocol uses bank-level TLS 1.3 cryptographic security to securely identify your car, authenticate your payment account, and start the electrons flowing automatically. It effectively turns the car itself into a secure, rolling digital wallet.
Now, I have to be honest with you. I have a major skepticism about this whole V2X vehicle-to-grid dream.
Let's hear it.
Look, I paid $20,000 for the massive battery pack in my car. I absolutely do not want to cycle that expensive battery pack every single day just to earn like $5 from the local power company. Won't constantly discharging my car into my house just totally kill my battery life over time.
That is a very mathematically valid fear to have. And this brings us right back to our battery chemistry discussion from earlier. If you bought a car with a high-end, expensive, high-nickel NCM battery, you probably want to be very careful about degrading it with daily grid trading.
Right.
But if you bought the cheaper mass-market vehicle with the LFP battery or the sodium-ion battery we talked about, those specific chemistries are incredibly physically robust. An LFP battery can easily handle 3,000 to 5,000 full charge cycles.
Oh, wow. So you could cycle it every single day for 10 straight years and barely make a dent in its overall health.
Exactly. The cheaper, highly durable battery chemistries are exactly what physically unlocks the commercial viability of these vehicle-to-grid features.
That makes a lot of sense. The chemistry has to match the use case. Now, before we leave the charging section, let's shift gears from passenger cars to something massive. The MCS, the megawatt charging system.
This is a completely different engineering beast. This is specifically designed for Class 8 commercial long-haul trucking.
Because if you have a massive semi-truck hauling 80,000 pounds of cargo with a gigantic 600 kilowatt-hour battery pack, plugging that into a standard Tesla supercharger would literally take hours to fill up.
It would take far too long. And in the commercial logistics world, time is literal money. A truck driver on the highway has a strictly legally mandated 45-minute rest break. That is their only window.
So the engineers have to figure out a way to fill that massive 600 kilowatt-hour battery from zero to full in exactly 45 minutes.
Which requires pushing an absolutely staggering amount of continuous energy. We are talking about sustained charging power well over 1 megawatt.
Hence the name.
Right. Specifically, they are pushing around 3,000 amps of electrical current through the cable.
3,000 amps. I mean, that is honestly terrifying. If something went wrong, an arc flash from 3,000 amps would literally vaporize you where you stand.
It is essentially trying to contain continuous lightning inside a rubber cable. The physical engineering challenges are just immense. To carry 3,000 amps without melting a standard solid copper cable would have to be literally as thick as your leg.
Which a human driver could never physically lift to plug in.
Exactly. So to keep the cable thin and flexible enough for a human to handle, they have to actively liquid cool the entire charging cable.
The actual cable you hold in your hands has coolant physically running through it.
Yes. Liquid coolant flows down the cable right alongside the high voltage wires. And the actual metal connector pins inside the plug itself are actively cooled so they don't weld themselves to the truck's charging port from the intense heat.
That is wild. But wait, think about the macro grid side of this. If a massive truck pulls off the highway into a rural rest stop and instantly demands over 1 megawatt of power on the spot, that is roughly the equivalent power draw of a small industrial factory turning all its machines on at the exact same second.
Yes, it is.
Wouldn't that massive sudden shock just completely crash the local rural utility substation?
It absolutely would blow the local transformers. So the charging stations themselves have to be fundamentally redesigned. They install massive buffer batteries physically buried on site at the station.
Buffer batteries. So the station has its own battery pack.
Yes. The station slowly, continuously trickles energy from the local grid 24 hours a day, slowly filling up its massive underground buffer battery. Then, when the semi-truck arrives and plugs in the station doesn't pull from the grid, the station's buffer battery rapidly dumps its stored power directly into the truck.
Well, that is brilliant. It completely isolates the fragile local grid from the massive instantaneous shock of the truck.
It acts as an energetic shock absorber. It is the only way megawatt charging is actually viable in the real world.
But honestly, hearing you talk about the extreme complexity of 3,000 amps, liquid-cooled cables, and massive underground buffer batteries just to charge a truck, it really makes me wonder if massive batteries are actually the right engineering answer for heavy-duty long-haul trucks in the first place.
Which perfectly leads us directly into our next pillar, section 3.6, the heavy-duty dual track.
The hydrogen story.
Yes. You are organically hitting on the exact structural divergence the report points out. For passenger cars, the debate is entirely over. Batteries have definitively won the war. But for Class 8 long-haul trucking, batteries suffer from a fatal flaw called the payload penalty.
The payload penalty, meaning the battery pack required to move a truck 500 miles is so physically heavy that you legally can't load as much heavy cargo into the trailer without violating highway weight limits.
And in the trucking business, carrying less cargo means you generate less revenue per trip. It destroys the profit margins of the logistics company. So as we approach 2026, the industry is actively embracing the dual-track strategy of hydrogen.
Now I feel like I have to express my skepticism again. Hydrogen feels like that one technology that is perpetually promised to be just 5 years away.
It has been the technology of the future for about 30 years now, but we're seeing a fascinating, highly pragmatic split in how hydrogen is actually being deployed right now. Track 1 is H2ICE.
H2ICE, meaning hydrogen internal combustion engine. Wait. We are literally talking about physically burning hydrogen gas inside a traditional piston engine, just lighting it on fire.
Yes, we are. And I know it sounds incredibly retrograde in a conversation about advanced solid-state AI
It
EVs.
honestly sounds loud.
It is loud, it rumbles, it has vibrations, but from a global supply chain perspective, it makes absolute total sense. Massive companies like Cummins are heavily pushing this pragmatic track
Why? What's the benefit of burning it?
because you get to take a standard, proven, heavy-duty diesel engine block that the industry has been building reliably for 80 years. You keep the same exact transmission, the same factory tooling, the same mechanic networks. You simply modify the direct fuel injection system, change out the spark ignition, and you just burn highly pressurized hydrogen gas instead of diesel fuel.
So it is incredibly cheap to mass produce because we already have thousands of factories that know exactly how to cast engine blocks.
Exactly. It requires radically low upfront R&D cost. It maintains the legendary extreme load durability of a traditional diesel engine. And crucially, the tailpipe emissions are completely zero carbon. It just exhausts water vapor and a tiny bit of NOx. It is the ultimate pragmatist's choice to decarbonize heavy industry rapidly.
Okay, I see the logic there. So what is track 2 then?
Track 2 is the fuel cell electric vehicle, or FCEV. This is the absolute purist's choice. Instead of burning the hydrogen, you create a highly advanced chemical laboratory on wheels.
How does that one work?
You use a complex proton exchange membrane, PEM for short. It chemically combines the solid hydrogen gas with oxygen sucked in from the outside air. That specific chemical reaction generates pure electricity, which then powers standard electric motors at the wheels.
So it's an EV that just happens to carry its own power plant. So you get total silence, no vibrating engine block, no moving parts in the power generation.
Yep. Total silence, massive efficiency, and the absolute biggest benefit is the refueling time. It takes about 15 to 20 minutes to completely pump the hydrogen tanks full, and you instantly have 600 miles of range again. It is the only true one-to-one operational replacement for a long-haul diesel truck that never stops moving.
But I'm guessing it's expensive.
It is wildly expensive compared to the combustion engine approach. The intricate catalyst plates inside that fuel cell membrane require high quantities of raw platinum to function.
Platinum.
Okay.
Yeah, that's going to drive the sticker price through the roof.
So we have this massive three-way fight happening in commercial trucking right now. You have cheap and dirty H2 ICE engines fighting against expensive and elegant fuel cells for the long-haul routes. And meanwhile, standard heavy batteries are actively squeezing both of them from the bottom by slowly taking over all the short-haul local delivery routes.
It's going to be really fascinating to see which standard actually wins out by the end of the decade. All right, let's move to our 7th and final pillar of the MECE framework. Section 3.7. You called this the glue holding the entire vehicle together. Thermal management.
Thermal management is honestly the ultimate unsung hero of the modern vehicle transition. In an old legacy gas car, managing heat was incredibly easy and almost an afterthought.
Right, because you literally had a controlled fire happening inside the engine block, constantly generating massive amounts of excess heat. If you needed to warm up the passenger cabin in the winter, you just blew a fan over the hot engine coolant. And if the engine got too hot, you just opened a simple mechanical thermostat and dumped the heat into a big radiator at the front of the car. Simple.
Exactly. You had practically infinite waste heat to play with. But in a highly advanced 2026 EV, the entire thermal paradigm is inverted.
How so?
Because modern EV powertrains, especially the Segesti inverters we talked about earlier, are so incredibly electrically efficient, they produce very, very little waste heat.
Which sounds like a good thing, right?
It is a good thing for range, but a terrible thing for passengers in the winter. Now you have a massive battery pack sitting directly under the car that ideally wants to be kept strictly around 25 degrees Celsius to perform optimally. You have a high-speed electric motor that can easily hit 100 degrees Celsius under heavy acceleration. You have an ultra-dense size computer chip hitting 150 degrees. And sitting on top of all of that, you have a human passenger who demands the cabin air be exactly 22 degrees.
That is a wildly complex thermodynamic balancing act.
It is, and since you don't have a hot engine block to rely on, you literally have to steal heat from one component to give it to another.
Energy harvesting.
Yes. The modern integrated thermal system is no longer just a simple radiator loop. It is one gigantic, unified, highly complex heat pump system. It uses an incredibly sophisticated multi-way routing valve, commonly called an octovalve, to actively shift thermal energy around the entire car in real time.
Walk me through a real-world example of how it harvests that energy.
Okay, say you are driving in freezing weather. The octovalve intelligently captures the tiny amount of waste heat being generated by the CC computer chips in the inverter. It routes that specific heat over to the main battery pack to warm the cells up so they can accept a fast charge efficiently. Or, if the battery is fine, it pumps that harvested chip heat directly into the passenger cabin to warm your feet.
It's literally a thermodynamic ballet constantly happening under the floorboards without the driver ever knowing.
It is, and the absolute newest, most extreme frontier in thermal management highlighted here is immersion cooling.
We briefly touched on this earlier when you talked about spraying dielectric oil directly onto the motor windings. But is the report talking about using this for the main battery cells too?
Yes. Actually physically dunking the live high-voltage battery cells directly into a flowing bath of engineered dielectric cooling fluid.
I mean, logically, that just sounds incredibly risky,
Yeah.
soaking electronics in liquid.
Dielectric means it doesn't conduct electricity so it won't short out the cells. And it is actually the absolute safest thermal method possible. It is the ultimate guarantee against thermal propagation.
Meaning, if one cell catches fire, it doesn't spread.
Exactly. If one single cell goes into thermal runaway and violently explodes, the surrounding liquid bath instantly absorbs the massive spike in heat energy. It completely suffocates the event. It stops the fire from spreading to the neighboring cell. It acts as an instant, highly effective chemical fire break inside the pack.
But there has to be a massive trade-off there. Doesn't filling a huge battery pack with hundreds of gallons of specialized fluid just make the car insanely heavy and expensive?
It adds significant weight and it is very expensive. But it also creates entirely new, complex material science challenges for the engineers to solve. The report explicitly mentions the required shift toward advanced high-performance thermoplastics, materials like PPA and PPS.
Why do we need new specialized plastics just to hold liquid?
Because if you use standard automotive rubber hoses or cheap plastics to pump highly engineered, hot dielectric cooling fluids around all day, the fluid would chemically degrade and rot the hoses from the inside out. So they have to fundamentally invent and scale up entirely new, non-corrosive, lightweight plastic polymer pipes to handle the extreme chemical environment.
Wow. Okay, so if we step back and look at the whole picture, we have built the ultimate 2026 vehicle today.
We have.
We have a highly customized solid state or sodium battery, depending on the price point.
Right.
We have an AI-driven predictive BMS brain living in the cloud. We have an 800-volt silicon carbide motor running at 99% efficiency. We have bidirectional VDG charging. Maybe we even have a heavy-duty hydrogen combustion engine for the logistics network. And the whole thing is kept from melting by a highly complex, intelligent thermodynamic heat pump system.
That is the complete MECE framework of the 2026 propulsion landscape.
So what?
Excuse me.
I mean, I have to ask the ultimate question here. So what? What is the fundamental takeaway for the normal person listening to this deep dive who just wants to go to a dealership and buy a new car in 3 years? Why does understanding this complex matrix matter to them?
The primary takeaway is the concept of optimization. The historical era of walking onto a lot and buying a generic one-size-fits-all vehicle is totally gone. We are rapidly moving into an era of highly specialized, bespoke mobility tools.
The multi-energy symbiosis you mentioned at the very beginning.
Exactly. But there is a deeper philosophical takeaway here regarding efficiency. The physical hardware components we discussed today, the massive bandgap of legaltine, the molecular structure of the battery chemistry, those hardware elements strictly set the absolute physical limit of what the car can do.
The hardware builds the box.
But the software, the AI, the digital twin, the cloud algorithms, the software is what actively exploits every single inch of that physical limit. We are officially witnessing the final industry transition from hardware-defined vehicle efficiency to completely software-defined efficiency.
It honestly makes it feel like the car is becoming less of a traditional mechanical vehicle and much more of a, I don't know, a massive rolling consumer device.
That is exactly the final provocative thought I really wanted to leave everyone with today. Think about everything we just systematically laid out. If the car in your driveway is actively functioning as a cryptographically secure payment wallet with plug and charge,
Right.
if it is acting as a highly profitable bidirectional power plant trading energy to stabilize the macro grid, if it is functioning as an edge AI data center constantly calculating resting entropy, at what point does the actual physical act of driving the car down the road become merely a secondary feature of the device?
Wow. Like how making an actual phone call is basically the least important secondary feature of my iPhone today.
Precisely. We are rapidly approaching the ultimate iPhone moment for the entire global powertrain industry. The mobility is just the chassis for the software services.
That is an unbelievable amount to process. My car literally might become more functionally useful and economically valuable to me just sitting parked in my garage trading electricity than it is driving me to the grocery store.
It might very well generate more actual passive daily value parked than driving. That is the reality of 2026.
Well, on that incredibly provocative note, we're going to wrap up this deep dive. Thank you so much for guiding us through this incredible complex matrix of technologies.
It is always a pleasure to sit down and unpack the future with you.
And to everyone listening out there, the next time you walk onto a lot to look at a new EV, don't just look at the leather seats and the curve of the sheet metal. Look at the raw spec sheet. Look deeper. See if you can spot if it has an LFP or a sodium battery. Check if it's running a true 800-volt architecture. Because the real revolution in the automotive world isn't happening on the dashboard. It's happening silently right under the floorboards. Stay curious, everyone, and stay charged.